Okay, so we were saying that if we take just lambda equal to 1, this means that I am not doing any relaxation. So no relaxation, because if lambda equal to 1, 1 minus lambda will be 0. So I'm just taking xi nu as it is. Now, in case my system is expected to diverge and I want to reduce this possibility of divergence, I can use lambda between 0 and 1. And more my system tends to diverge, smaller should be lambda. Because by using a small value of lambda, I will take a small proportion of the updated value and a larger proportion of the old value. Okay, so if you see that your system is tending to diverge, try to use, you can lower lambda. As you lower lambda, you can enhance the possibility of convergence. Okay, now on the other hand, if your system seems to converge in a very fast way and convergence behavior is fine, then you can say, why to not accelerate convergence? In this case, you will take lambda between 1 and 2. So you will take, then you will increase the percentage of new compared to old, and you will use a negative percentage for the old value and a positive percentage for the new value. And for example, you can say, I will update the value as, if you take lambda, for example, 0.5, so you will have 150% times x new minus 50% times x old. Okay, and in this way you increase the update if you want, and the update will be faster in this way. So whenever lambda is between 1 and 2, we say that we are performing over relaxation. Okay, and this will accelerate the convergence of an already convergent system. So pay attention. We use under relaxation when we have a non-convergent system and we want to try to converge it. And also, if we have damping oscillation in the solution, then the convergence is not certain. Then we can use under relaxation. On the other hand, if already we have a system that is converging and we want to try to accelerate its convergence, we use over relaxation. So as you can see, the selection of lambda is very dependent on the problem. And in general, it's determined by experience, empirically. So hopefully after, if you do graduate studies, if you are performing CFD simulations to solve for the thermal field, the velocity field, the concentration field in a space, then you will see that it's a very complex problem. And sometimes I should use under relaxation factors to allow convergence of my system. And even sometimes if the behavior is highly divergent, sometimes even under relaxation with very small lambdas will not work. But in majority of cases, it will work. Okay?
دكتور
Yes.
هو نفس الشيء، هو مثل كانوا إذا مثلا it converges عم جرب بعد الأكسس عن بعضهم تأوصل أسرع. في possibility to diverge عم بحاول أقرب الأكس. تمام.
Exactly. This is the idea. Okay.
Doctor?
Yes.
Doctor, can you please repeat what you said about the 50%?
Yes, of course. I'm telling you, if you have fast convergence and you want to converge in a faster way, you can take lambda between 1 and 2. So if you take lambda 1.5, what does that mean? If the value of lambda is 1.5, this means that when you update xi, you are taking 150%, which is 1.5 of xi new, okay, minus 50% of xi old. So you are increasing the weight of update of your value. And instead of just taking it as xi new, you are taking a value that is closer to يعني much more closer من الابديتد. يعني انت عم بتزيد الeffect of the update. You are هون كان الويت when you just take xi new, الويت تبع xi new هو 100% والويت تبع xi old هو 0%. When you do over relaxation بيصير الويت للx new 150%. يعني you are increasing the weight of xi new and you are decreasing the weight of xi old. يعني عم بتبعد اكثر الابديتد فاليو عن الاولد فاليو. This is why it's called over relaxation.
It's clear. Thank you, doctor.
Okay, welcome. So now, let us consider an example where we want to solve the system with Gauss Seidel using over relaxation with lambda equal to 1.2 and a stopping criterion of epsilon s equal 10%. So here also they specified the method to use. We want to use Gauss Seidel method, and we want to do over relaxation. So the only modifications that we will do in this problem compared to the previous problem we have seen together is that every time we update my solution, I find x1 and x2 new, I should at the end do the over relaxation. I should take 1.2 of the updated value minus 0.2 of the old value. So let us see how. First, we can start by writing this system into equation form. And always, when it's possible to achieve diagonal dominance, do it. And here, for example, the elements on the diagonal are not dominant. 3 is smaller than 12, and 2 is smaller than 10. So if I just do pivot of these two rows, now I get a diagonally dominant matrix. 10 is larger than 2, 12 is larger than 3. So I am sure that the system will converge. Okay. When I am sure of, yes.
هيدا الدياجونال هي مثل كأنه عم we're ensuring إنه pivot elements هن أكبر شيء.
هلا هون ما في pivoting بس yes exactly. And if you want to solve for this system هلا if you want to solve it with conventional method, yes exactly. يعني أنت when you do this will ensure إنه pivot elements هن الأعلى شيء. This is why this justified convergence. Okay, بس نحن ما حنعمل هون pivoting، ما حنعمل Gauss elimination. We will solve for the system using iterative techniques. Okay?
Yes, sir.
Okay. So now this is the updated system. Now I can just get x1 by using the first equation, يعني 10x1 minus 2x2 equals to 8. So now if I take x2 to the other side and I divide by 10, then I get 0.8 plus 0.2x2. Now I start with the initial guess. The initial guess is 0. Then I have the updated value for x1 is 0.8. But now I should not forget that I should apply relaxation for x1. So now I apply relaxation for x1. So I multiply the new value by the relaxation factor, which is 1.2. And I multiply the initial, the previous x0, if you want, which is the initial guess here. I multiply it by 1 minus 1.2. So here, for this relaxation, the coefficient of x1 new is 120%, while the coefficient of x old is minus 20%. So this is an over relaxation. Okay. And then now, this is my updated value of x1 for the first iteration. I take the value after relaxation. Okay. Now the next step is to compute x2. So now when I compute x2, I will take the relaxed value for x1, which is 0.96. Okay. So now I will use the second equation. So all I have to do here is to use the second equation. The second equation is, you can here directly use the formulas, and until you develop formulas, you can directly use them. In the slide, I will go back to the slide. You can use the blue slide to directly. هلا أنا بعملكم إياهم to remember. If you forget, you can directly find it. Minus 3x1 plus 12x2 equals to 9. So now if you rearrange your terms, you have that x2 is equal to 3x1 plus 9 over. So since we are using the Gauss Seidel method, then we should use the updated value. ومش حيلا updated the relaxed one. يعني نحن we did first update of x1 and then we applied relaxation. We will use this final updated value in computation of x2. Okay. So now we will replace x1r here, the relaxed value. So now we, once we are done with x2, we don't forget to apply also relaxation for x2. So the relaxed value for x2 is 1.2 times the new value plus 1 minus 1.2 times the old value, which is here 0, because this is the initial guess. We are at the first iteration. Then we get the updated value of x2 relaxed. Okay, so now we get x2 relaxed. Now we are ready to move to the second iteration. So we will repeat the same procedure. So now, first, to get x1, we will use the old value of x2. Once we get x1, we do relaxation for x1. So here in this step, we have a relaxation of x1 by just doing 1.2 times the updated value of x1 minus 0.2 times the value of x1 from j equal 1 in the previous iteration, which is 0.96. Then once we updated x1, we have x1 relaxed. Then we will use it into the computation of x2. And once we get x2, we don't forget to apply relaxation on x2 to get x2r, which will be used now for computation of x1 in the third iteration. And we repeat this procedure. And at each step, we should verify the error. We should make sure for the error if it's converging or not. So here, for example, we should do it in each step, of course. Okay. So here, if by comparing the error after doing the iteration, we get that we have an error here of 7% for x1, and for x2 it's 2%. So if the criterion is 10%, then we are done. Okay, we are done with this system. So in 3 iterations, we were able to reach the criterion of convergence. If you try, مثلا, here to use Jacobi method without relaxation, you will see that you will need maybe more iterations to reach a solution, because the over relaxation وهون كمان الجاس سايدل will accelerate also. Already we are using Gauss Seidel, which accelerates convergence, plus we are using over relaxation. So we expect this will require much less iterations than if we just do Jacobi method without over relaxation. Any question on this before we proceed? Okay. So until now, all methods developed were for a linear system. We have seen in chapter 9, 10, and 11 several methods: Gauss elimination, LU factorization, inverse method, and now we have seen in this chapter Gauss Seidel and Jacobi method. For all are for linear systems. What if we have non-linear systems? What is good about iterative methods is that it will work. Iterative methods will work for linear and non-linear systems, while in general the method developed previously were specific for linear systems. Okay, so now we will see the multivariate Newton-Raphson method, which is a method used to solve nonlinear systems. And why we are using Newton-Raphson? Because as you recall in chapter 6, this method is characterized by a quadratic convergence. So once it's converge in a very fast way. This is why we will develop now a general method of Newton-Raphson for multivariate systems, not only f of x. So in chapter 6, we just solved, we had f of x equal to 0. In this chapter, we will see that if we have a function having several variables, so here if we have a function of x and y, and we want to find what is the couple x and y for which f of xy equals to 0, we will use a multivariate Newton-Raphson method. So first, a good start to estimate nearly the solution is to do a graphical representation. So if you represent, for example, the following 2 functions, the first one has variable x1, x2, and also the second one has variables x1 and x2, and we set the functions equals to 0. If we draw the functions, we take several points of each and we draw them. They will intersect at a certain point. This is the solution of the system. So we can expect nearly the range of solution. But if, as I told you in Newton-Raphson, when we did Newton-Raphson method, in case we want to find the exact solution, okay, we need to develop method. We don't have just to use a graph, because a graph will not give us a very accurate result. So in case we need to have high accuracy, then we should do calculation, numerical calculation. So what is the idea? The idea is very close to the idea we developed in chapter 6. So if you recall from chapter 6, in chapter 6 we got the estimate of the root xi plus 1 as xi minus fxi over f prime xi, where f prime was the exact derivative. So we derive function f. Now we want to develop a similar technique, but now with functions with multivariable. So what we will do, we will first find the expression of the function when we develop it using Taylor series expansion for multivariate system, and then we will do the same technique, which consists on setting f and the function f equal to 0, because what is our purpose at the end? Our purpose is to find x and y for which f of xi plus 1 fy plus 1 equals to 0. So when we set these equal to 0 and we rearrange terms, and we take xi plus 1 yi plus 1 terms to the left hand side, and we keep terms function of xi yi on the right hand side, we will obtain a system which will give us the updated values. So I will repeat. We are following the same procedure as we did in derivation of Newton-Raphson in chapter 6. The first thing to do is to write the expansion of xi plus 1 around xi using Taylor series and doing truncation. So after the first derivative term, we do truncation, so all other terms will be neglected. Then we say our purpose is to reach the value of xi plus 1 for which fx prime plus 1 is 0. So we can do an estimate based on this method. Why it's an estimate? Because we have a certain error due to truncation. Okay. So to find the value of xi plus 1 for which f is 0, a good approximation will be to say that 0 is equal to fxi plus xi plus 1 minus xi times f prime xi. And then once we put this equation, we rearrange terms. Since we want to find xi plus 1, we take xi plus 1 to the right hand side. And we keep other terms on the left hand side, on the بالعكس. We take xi plus 1 to the right hand side, and we keep these on the عم غلط فيهم. xi plus 1 باخدها على left وهديك بخليها على right. Okay. And then I get the following function. I get xi plus 1 is equal to xi minus fxi over f prime xi. Okay. هلا when I take xi plus 1 to this side بتصير minus, فبرجع بقلب الساينز, I get this equation. Now I will do the same procedure here. I will just do the expansion first of xi plus 1 yi plus 1 using Taylor series expansion, okay, around xi yi. If I do so, the only difference here, in this case, the variable was only x, so I multiply by f prime x. While here I have two variables, so I should do partial derivatives. So I can say that from Taylor expansion, fxi plus 1 yi plus 1 is equal to fxi yi plus xi plus 1 minus xi times del f by del x at point xi yi plus yi plus 1 minus yi times del f by del y على xi yi. Okay. And now once I do this, I will write it for function f because I have two functions, and I will write it for function g. And now once this is done, I say I want to find the solution. So I want to set this equal to 0 and this equal to 0. And now I will rearrange my terms in a way to have xi plus 1 terms and yi plus 1 terms from the left hand side, and xi and yi terms from the right hand side. I will do it for both equations, and this will give me the following system. So by just setting these functions to 0 and rearranging terms, this is the left hand side with terms of xi plus 1 yi plus 1. This is the right hand side in terms of xi yi. And I will do it for both equations. So now, if I look at my system, I have a system of two equations with two unknowns. So I can rearrange my system in a matrix form. So the coefficients multiplying xi plus 1 will constitute the first column. So I have del f by del x and del g by del x for the first column. For the second column, I have del f by del y, del g by del y. This is a Jacobian because you know that the Jacobian will give me the partial derivatives of a function with respect to all of its variables. So here, this row is for the partial derivatives of f, and this row is for the partial derivatives of g. Okay, and now I was able to make my system linear. And my system was a non-linear system. I made it linear by the following operation. And now to solve for xi plus 1, yi plus 1, I can use several techniques. All techniques developed to solve a linear system can be used here. You can use Gauss elimination. You can use calculator if you want, because it's two equations, two unknowns. You can use LU factorization. You can use A minus 1. What is the A minus 1 technique? You know that A, matrix A times X equals to B. So if I just find A minus 1, if you find the inverse of A and you multiply just A minus 1, so if I put A minus 1 here and I put A minus 1 here, A minus 1 and A will cancel out because they should give me the identity matrix. So these will cancel. And then I can say that matrix X is given by A minus 1 times B. Okay, so if I find the inverse of A, I can use this technique to get B. And if you remember, we said that this is a decoupling method because it will allow me to solve for any X without knowing the other. Not like Gauss method where I need to do a backward elimination, and not as LU factorization where I need to do forwards and backward elimination. Here, I can directly have equations of x1, x2, x3 function of B, and they are decoupled from each other. This is the advantage of using the inverse of a matrix. So now, when I write this system, I will have the Jacobian matrix times the vector of updated values of x and y equals to, from the other side, when I did comparison, this is the other side. So I have here minus the value of the function at xi, yi in the previous iteration, plus xi old times del fi by del x, plus yi old times del fi by del y. And I have the same term model for the second row. So minus ji plus xi del gi over del x plus yi del gi over del y. So now I got my general term for B. To understand it better, let us apply it in a numerical example. So we will give in this example the following system of equations, and using the multiple equation Newton-Raphson method to find the roots with initial estimates x1 equal 1.5 and x2 equals to 3.5 and a stopping criterion of 10%. So to start with, please, this is very important, never keep the system in this form. You should transform it to a function equal to 0 and here a second function equal to 0. So all you have to do is to take here 10 to the left hand side, or to take x1 square and plus x1, x2 to the right hand side. Okay, both are right. The important is that you end up with a function equal to 0. And you do the same for the second term. So you can take minus 57 to the left hand side. And then you get f2 x12 equals to 0. Now, the second step will be to set up the Jacobian matrix and evaluate for initial estimates to start doing iterations. So first, the Jacobian matrix, to get it, all I have to do is to do the partial derivatives of each function with respect to the two variables x1 and x2. So I will start with derivative of f with respect to x1. When you do the derivative of f with respect to x1, you consider x2 as a constant. So here, for example, this term, its derivative will be 2x1. And this term, its derivative will be x2. So 2x1 plus x2. Now, second term is the derivative of f with respect to x2. When I derive with respect to x2, x1 is a constant. So x1 squared is constant. So derivative is 0. And plus x1, x2, since x1 is a constant multiplying x2, then the derivative of x1, x2 is x1. So just for del f1 by del x2, the derivative is just x1. Now to proceed, I move to the second function. I want to find its partial derivative with respect to x1 and its partial derivative with respect to x2. when I derive with respect to x1, this is constant. I don't. It's like a constant, so its derivative is 0. The derivative of this term is, since x2 is treated as constant, so it's 3x2 squared. And finally, when I derive f2 with respect to x2, this is x2, so this is the first term is 1 plus here I have x2 squared, the derivative is 2x2, and I have it's multiplied by a constant because I consider x1 constant when I derive with respect to x2. So I will have the derivation is 3x1 times 2x2, which is 6x1 times x2. Okay, now I am done with the Jacobian, and I will use it in any step. So I always should find the general expression of the Jacobian because I have to replace in each iteration. So now in the first iteration, I will use the initial estimates, the initial guess for x1 and x2. So all I have to do now is to replace x1 and x2 by their values in the Jacobian matrix to get the Jacobian matrix at the first iteration. Now, in addition, I need to compute the values because I need in the prediction of B's vector B, I need to know the value of the function at these points, at the initial guess. So I should replace x1 by x2 into here, into the expression of the functions f1 and f2 to get the values of f1 and f2 for this guess, for the guess I made. Once this is done, I can now compute vector B, because the right-hand side vector is given by the following general expression. It's minus f1 at the point considered. Okay, so here I used the initial guess to assess what is the value of f1. It was minus 2.5, and since I have minus here, it becomes plus 2.5. Now, x1 is the value given at this iteration, so this is here the initial guess. Del f1 by del x1, I use it from Jacobian matrix because I have assessed all terms. So this is the first term of Jacobian. First, so this is, if you want, 1, 1. This is terms G11. Okay. This is term G12. This is term G21, and this is G22. I have calculated all of these terms for the initial guess. So all I have to do now is to replace numerically to get the right-hand side vector. Once this is done, now I have just to solve a linear system. And here I can do the method that I want. It's not specified. Please, if I specify for you the method to use in the exam, you don't have the right to use another method. So if I don't tell you use any specific method, you can use here the calculator to solve for x1, x2. If I tell you use LU factorization to solve for your linear systems, then you should respect this. So you can use Gauss, you can use LU, you can use the inverse. So here they did the inverse method. They said that x1, x2 can be given by the inverse of this matrix times B vector, and they got the solution. Now, once you get the solution, as usual, you should check for your relative error. And if it doesn't satisfy the stopping criterion, you should continue to perform iterations. So now let us move to the second iteration. We are repeating the procedure. The only thing that is varying is x1 and x2. So now we will replace x1 and x2 by the updated values we got in the previous iteration. So from previous iteration, we got that x1 is 2.036 and x2 is 2.844. So now all we have to do is to replace these values first in the Jacobian matrix to get the updated Jacobian matrix at the current iteration. Then we replace into the expression of functions f1 and f2, we replace x1, x2 by the updated values to get the updated f1, f2 values. And once we are done with the Jacobian elements and f1, f2, we need them to compute the right-hand side vector. So here all we have to do is to replace f1 by minus 0.0643. We replace x1 by the value of x1 we got from the first iteration, and del f1 by del x1 is 6.916. It's the first element of the Jacobian. X2 is the solution for x2 we got in iteration 1, because now we are in iteration 2. So we just choose for x1, x2 the values in the previous iteration. Now for del f1, del x2, it's the second, it's element G12 of the Jacobian. So we replaced by 2.036. Then now we can get the first element of B vector. Now we'll repeat the same procedure to find the second element. So we replace F2 by minus 4.75. We replace X1 by its value from first iteration. We replace del F2 del X1 by 24.27. We replace X2 by the value we got. So here for X1 and X2, just remember I use the value from previous iteration. So for X1, 2.036, for X2, 2.844. And then I am ready to calculate all elements of B. Now, once I have everything, I will update my linear system. My new linear system is the following one. So also here I can use any method to solve for X1, X2. I get the updated values of X1, X2, and now I check for the relative error. Since for both variables, the relative error is below 10%, then I can stop here and say that my solution is converged. If the criterion was more strict, so if we had to solve, for example, for 1% stopping criterion, then we should continue to iterate. Let me check if you have questions. Said, it depends if they asked you to apply relaxation or not. Here, they didn't ask to apply relaxation. If they told you, no, use relaxation, you can use it here also, same concept. Okay, so here they didn't say to apply any relaxation. In case they told you use, for example, over relaxation, all you have to do is once you find X1, X2 here, your final solution, and you should first find both the updated values of X1, X2. Once you find them, you say, if they define for you an over relaxation factor of, for example, 1.3, then you say, I will take X1 relaxed equals to X1 new, okay, which is here 2.036 times 1.3 minus 0.3 times X1 old. So here, for example, X1 old is the gas. So from the gas, X1 was 1.5, okay? So just the procedure, if you have to do over relaxation or under relaxation, is first to solve for X1, X2, okay? And then once you solve for them, you apply relaxation. Here, it's not like Gauss Seidel. Gauss Seidel, you are using the updated value of X1 to get X2. No, you are solving just a linear system, okay? If you decouple them, if you decouple the solution of X1, X2, then you can find already if you decouple هيكونوا independent, okay? If you have other techniques, Gauss or if you do forward elimination or backward elimination in case of Gauss, and in case of LU use forwards and backward, then ساعتها بيصير فيك تعمل كمان relaxation بالcomputation. يعني لأنه أنت if you use backward elimination, you find X2, then you find X1. ساعتها فيك تعمل الابديت على الريلاكسيشن، يعني من بعد ما تلاقي X2 أول شيء تعمل لها ريلاكسيشن، بترجع you use it to update X1، بترجع بتعمل ل X1 relaxation. In this way you can do مثل ما عملنا previous Gauss Seidel example. But in case here you use a decoupling technique, then you will find X1 لحال, X2 لحال. Then at the end, once you find X1, X2, you relax them. So this will be clarified in the problem. What should you do? And which method you should use. Okay?
Doctor?
Yes.
When calculating the approximate error, بناخد ال values اللي عملناهم relaxation ولا اللي بلا relaxation؟
إذا عملت relaxation أكيد بدك تاخد ال values مع relaxation.
Yes.
Okay.
Okay.
وإلا ما لها معنى، يعني ما أنت لا عم تعمل relaxation تتسرع ال convergence.
Yes.
So of course you take بالrelative error you take relaxed values.
Okay, doctor. Thank you.
Welcome.
Doctor,
Any other? Yes.
if we want to do the relaxation بس على الجاكوب بصير هونيك بدي أعمل بين الجديدة هي مع الانيشال جاز.
لا إذا عم تستعمل جاكوبي ميثود، المفروض أول شيء بتجيب الابديتد values x1 x2 x3 بترجع بتعمل لهم ريلاكسيشن. عرفت كيف؟ يعني انت لانه شو فكره الجاكوبي؟ الجاكوبي ما بتعمل يعني مثلا تنرجع على السكيم هون. This is the general scheme. انت اذا عم تعمل جوس سايدل x1 حتعمل لها اول شيء حتجيب الاكس 1 ابديتد لانه رح ترجع تستعملها باكس 2 تعمل لها ريلاكسيشن قبل وبترجع بتستعملها باكس 2.
Yes.
بينما بالجاكوبي ميثود اصلا you are not using الابديتد x1 يعني انت حتجيب x1 ما حتستعملها باكس 2 حتجيب x2 ما حتستعملها باكس 3. يعني بالجاكوبي ميثود اول شيء you find x1 x2 x3 بترجع بتعمل لهم ريلاكسيشن.
Okay, يعني at each iteration.
Exactly.
Yes.
بينما هون لانه حتعوزها بال2 تعمل لها ريلاكسيشن قبل وبترجع بتستعملها بال2. تستعمل الريلاكسد فاليو بال2 ساعتها.
Yes, exactly.
Yes.
Thank you, doctor.
وهون بالاكس 3 بتستعمل الاكس 1 ريلاكسد واكس 2 ريلاكسد.
Yes, مظبوط. Relaxed.
Yes. بينما here after you get them بتجيب x1 relaxed x2 relaxed x3 relaxed بتستعملهم now الريلاكسد فاليو بالnext iteration. Okay?
Yes. Thank you, doctor.
Welcome. Any other question? Okay, so we are done with this chapter. Tomorrow we'll correct the assignment and start a new chapter. Thank you.